Welcome to our guide on mastering advanced regression tools in EViews. Today, we'll explore techniques that go beyond basic ordinary least squares to build more robust and realistic economic models. We will cover polynomial distributed lags, robust standard errors, weighted and nonlinear least squares, and indicator saturation. These powerful tools are essential for refining the lens through which we view economic data, enabling us to capture more complex relationships and address common data challenges. But before we dive into these solutions, let's first understand the problems we often face when dealing with real-world economic data. The classical assumptions of ordinary least squares, or OLS, paint a picture of a perfect world. However, real economic data, such as GDP, wages, or stock prices, is rarely perfect. It's often quite messy. This messiness manifests as common problems like heteroskedasticity, where error variance isn't constant, serial correlation, where errors are dependent over time, nonlinearity, where relationships aren't straight lines, and structural breaks, or outliers, which are sudden shifts or extreme observations. Ignoring these realities leads to biased coefficients and unreliable hypothesis tests. When our model specification doesn't truly match the data-generating process, we encounter misspecification. In such cases, OLS is no longer the best linear unbiased estimator, or BLUE, meaning our estimates lose their desirable statistical properties. For example, if we model electricity consumption against income and find increasing error variance, ignoring this heteroskedasticity would lead to inefficient estimates and incorrect standard errors. So, how do we navigate this complex landscape? Let's now explore a decision map to guide our modeling choices, starting with proper model specification. The first crucial step in building a robust econometric model is thoughtful specification. This decision map helps us determine how our variables relate based on economic theory, guiding us to the right tools. First, if we suspect lagged effects over time, meaning an action today impacts an outcome gradually, polynomial distributed lags, or PDLs, are ideal for capturing these dynamic responses. Second, for categorical or group differences, like regions or demographic segments, EViews @expand function automatically creates the necessary dummy variables, simplifying the process and ensuring proper accounting for group-specific impacts. Third, when relationships are inherently nonlinear in their parameters, such as a production function, Nonlinear Least Squares, or NLS, provides the direct estimation method for these complex functional forms. These powerful specification tools, with their corresponding syntax like PDL of x, n, and d, @expand of x, and y equals c1 times x to the c2, are all integrated within EViews' standard equation estimation box. Once we've specified our model using these methods, our next step is to diagnose its residuals for any remaining issues. After we've specified our model and run the initial regression, the next critical step is to check its diagnostics by examining the residuals and overall structure. This decision map guides us through common issues and their solutions. First, if we detect heteroskedasticity, meaning our errors have non-constant variance, we have two primary approaches. We can use weighted least squares, or WLS, which transforms the model by giving less weight to noisy observations, or we can simply adjust our standard errors using White's heteroskedasticity consistent, or HC, method. Next, if we find serial correlation, where errors are correlated over time, especially common in time series data, we turn to HAC, or Newey-West, standard errors. These are robust to both heteroskedasticity and autocorrelation. If correlations are present within grouped observations, such as students within schools or firms within an industry, then cluster-robust standard errors are the appropriate choice to ensure valid inference. Finally, for unknown structural breaks, perhaps due to an unobserved policy change or economic shock, the indicator saturation method offers an automated, objective way to detect and account for these shifts. You can access most of these robust covariance methods and WLS options within EViews by navigating to the Equation object, then Estimate, then the Options tab, and selecting Covariance Method. It's crucial to remember that correcting standard errors with methods like HAC or White does not alter your coefficient estimates. It only corrects the t-statistics and consequently the p-values, leading to more reliable hypothesis tests. Polynomial distributed lags, or PDLs, address high multicollinearity that arises when we include many unrestricted lags of a variable. This often makes individual coefficient estimates unreliable. The PDL solution is to constrain these lag coefficients to lie on a smooth polynomial curve, effectively reducing the number of parameters and offering a clear, more stable view of the dynamic impact. For instance, PDL of orders 8, 3 would model the effective orders over 8 lags using a third-degree polynomial. Turning to categorical variables, manual coding of dummies is tedious and error-prone. EViews simplifies this with the @expand function. It automatically generates dummy variables from a categorical series, such as @expand of sex for gender. Remember, it's essential to use @drop_last or similar methods to avoid the dummy variable trap, ensuring your model remains well specified. These tools help us correctly specify the mean equation of our model. Next, let's explore how to ensure our statistical inference is correct, even if the error terms aren't perfect. The sandwich estimator approach adjusts standard errors to be robust against violations like heteroskedasticity and autocorrelation. Crucially, it doesn't change coefficient estimates, only correcting standard errors, t-statistics, and p-values for valid inference. We primarily use 3 types: White's HC errors for heteroskedasticity, HAC Newey-West errors for both heteroskedasticity and autocorrelation in time series, and cluster robust errors for correlations within groups in panel data. The table powerfully illustrates this. A coefficient significant under standard OLS with a t-stat of 4.2 can become insignificant with a t-stat of 1.7 after applying HAC robust errors due to an increased standard error. This prevents false conclusions. A critical note: HAC estimators require large samples to be valid. In small samples, they can be misleading. In EViews, access these options via Estimate, Options, Covariance. Correcting standard errors is one solution. Next, we'll explore changing the estimation method with weighted and nonlinear least squares. Today, we're diving into 2 powerful estimation techniques: weighted least squares, or WLS, and nonlinear least squares, or NLS. WLS is a method used to address heteroskedasticity, where the variance of your errors isn't constant. Instead of just correcting the standard errors, WLS actively transforms your model by assigning lower weights to noisier observations. This process leads to more efficient and precise coefficient estimates. When setting this up in EViews, you'll specify your weighting series, and a helpful tip is that EViews scales these weights by default so they sum to your total sample size. Conversely, NLS is employed when the relationship you're modeling is fundamentally nonlinear in its parameters, preventing the use of standard OLS. For instance, estimating a Cobb-Douglas production function like y equals c1 multiplied by x raised to the power of c2 requires NLS. In EViews, you directly type this nonlinear formula into the equation specification box, and the software uses iterative algorithms to find the best parameter estimates. These methods allow us to tailor our estimation approach to the specific characteristics of our data and the underlying economic theory. Now, let's turn to a very modern and powerful technique for dealing with an often overlooked problem: unknown structural breaks. Indicator saturation, or ISAT, is a powerful technique rooted in the general to specific, or GETS, modeling approach. Its primary goal is the automated detection of structural breaks and outliers in your data, without requiring you to pre-specify their timing. The method begins by conceptually saturating your model with a dummy variable for every single observation. While this sounds impossible to estimate directly, EViews algorithms then intelligently and systematically prune these, retaining only those dummies that are statistically significant and essential for capturing major shifts or breaks. The true value of ISAT lies in its objectivity. It eliminates the researcher bias often associated with subjectively identifying crisis dummies, as the algorithm itself identifies these critical points based solely on the data. For instance, in our GDP growth chart, ISAT would automatically pinpoint and account for sharp downturns, such as those in 2008 and 2020, leading to a cleaner and more accurate model. The main hub for implementing all these advanced econometric techniques in EViews is the equation estimation window. This central interface allows for both graphical interaction and direct command input. First, the specification area is where you define your model. Here, you'll enter your dependent and independent variables, and also integrate specialized functions such as @expand for automatically generating demi-variables from categorical data, PDL.lags for distributed lags, or even fully define a nonlinear equation for nonlinear least squares estimation. Below that, the method dropdown lets you select your primary estimation technique. While least squares is the default, EViews offers other options like robust least squares or stepwise. Crucially, the Options tab is your gateway to many of the advanced tools we've discussed. This is where you can specify robust covariance methods like White's heteroskedasticity consistent errors, or HAC, and configure weighted least squares. For those who prefer efficiency, EViews also provides powerful command line shortcuts. For example, you can directly type equation eq1.ls cov equals HAC y c x into the command window and press Shift-Enter. This single command will create an equation named EQ1, estimate it using OLS with y as the dependent variable and c and x as regressors, and automatically apply HAC robust standard errors, bypassing the menus entirely. Welcome back to our deep dive into EViews' equation estimation window, specifically the crucial Options tab. This tab is your gateway to fine-tuning many advanced regression techniques. First, under the Coefficient Covariance Matrix section, you can select your desired robust standard error method, White for heteroskedasticity, HAC for both heteroskedasticity and autocorrelation, or cluster for within-group correlation. It's critical to note that if you choose cluster covariance, you must also provide the ID series for defining those clusters in the active field. Also, the full HAC options only become visible once HAC is selected. Next, for weighted least squares, or WLS, you define the weight series here. This allows you to apply different weights to observations, often to correct for heteroskedasticity by giving less weight to noisier data points. Finally, for iterative estimation methods like nonlinear least squares, or NLS, the iteration control section allows you to set parameters such as the maximum number of iterations and the convergence criterion. This ensures the algorithm finds a stable and accurate solution for your nonlinear model. Let's look at a practical example. Suppose we want to model the logarithm of wages based on age, sex, and region. Sex and region are categorical variables. Instead of creating dummies manually, we use the command ls ln wage c age @expand sex @expand region @droplast. The @expand sex creates dummies for each category in sex, and @expand region @droplast does the same for region but drops the last category to serve as the reference group, thus avoiding the dummy variable trap. As you can see in the output, EViews automatically generates the dummy variables like sex equals 1 and region equals north. This makes the code clean, readable, and less prone to errors. A key benefit of this approach is that it makes it very easy to perform walled tests on groups of coefficients, for example, to test if all the region dummies are jointly equal to 0. In the results, the coefficient for sex equals 1 would represent the wage differential for that group compared to the reference group, sex equals 0, holding age and region constant. It's crucial to always be aware of your base group when interpreting the results. Next, let's see a case study where the error term itself is the problem and how we can fix it with weighted least squares. Here, we delve into a scenario where we're addressing heteroskedasticity using weighted least squares, or WLS. The core idea is to correct for non-constant variance by assigning less weight to observations that are noisier or have higher variance. This approach makes the coefficient estimates themselves more efficient and precise. As you examine the EViews output, you'll see two distinct sections, weighted statistics and unweighted statistics. It's crucial for accurate hypothesis testing that you always refer to the weighted statistics section for your t-statistics and p-values, as these reflect the transformed, more efficient model. Also, note the r-squared values. The weighted r-squared accurately reflects the goodness of fit for the transformed model, where heteroskedasticity has been addressed, offering a more relevant measure of fit than its unweighted counterpart. This weighting process effectively reduces the influence of noisy data points, leading to more reliable estimates. Now, let's examine a different problem common in time series, serial correlation, and how HAC errors provide a solution. Our scenario involves a time series model that exhibits serial correlation, often indicated by a low Durbin-Watson statistic. This violates a key OLS assumption, making our standard errors unreliable. The action we take is to switch from standard OLS errors to HAC, or Newey-West, robust standard errors. Crucially, this does not change the coefficient estimate, which remains at 1.5. However, the key change is in the standard error. It increases significantly from 0.02 to 0.08. This larger standard error reflects the additional uncertainty introduced by the serial correlation. Consequently, this leads to more conservative inference, with the probability, or p-value, jumping from a highly significant 0.001 to a much less significant 0.150. The takeaway is that we are now more confident that our original significance result wasn't just an artifact of uncorrected serial correlation. For instance, if this was a model of stock returns, failing to use HAC errors might lead you to believe a trading strategy is profitable, when in fact the perceived significance is spurious and disappears once the standard errors are correctly calculated. In this case study, we combine two powerful techniques: Nonlinear Least Squares, or NLS, and indicator saturation, or ISAT. First, for NLS, we're estimating a Cobb-Douglas production function, where GDP depends on investment, INV, with the model specified as GDP equals C1 times INV to the C2. EViews employs iterative algorithms such as Marquardt to find optimal values for C1 and the elasticity C2. A critical aspect of NLS is ensuring convergence. If the model fails to find a stable solution, it's essential to check and adjust your starting values for the coefficients. Turning to ISAT, we often encounter unexpected, massive shocks and residuals, like the one evident in 2008. While one could manually add a dummy variable, ISAT offers an objective and automated solution. By applying the ISAT procedure, the algorithm identifies such a shock and creates a specific variable, shift 2008, which effectively absorbs its impact. As shown in the graphic, this process significantly cleans structural noise from the residuals, leaving a much more well-behaved error term for further analysis. This objective cleaning is the true power of ISAT. We've covered a comprehensive set of advanced regression tools in EViews. I want to sincerely thank you for following this guide on mastering these techniques. As we've emphasized throughout, data speaks, but only if you have the